So, let me introduce our next speaker. It's Gerrit Groenhof from Nanoscience Center of Chemistry in the University of...
Yeah.
And I will not try, sorry. And he will talk today about modified photodynamics under strong light matter coupling, polaritons, or an optical illusion. We're very curious to hear what he has to tell us.
Okay, that's nice to know. I would like to thank first, of course, the organizers for setting up this meeting. I have seen things that I have never thought about, and that is something, food for thought. And yeah, so now what we're going to talk about today is a bit different. It's chemistry. You're going to see some bonds break and form. You're going to really see it. But first, the question I like to make at the start of my talks is to point out where I'm working, which is Jyväskylä. But here in Finland, I think that joke will not make any impact. So what I do like to say, the field in which this talk, the context of this talk is polaritonic chemistry. And there the only thing that matters is correlation. Causation, nice to have, but not needed to publish. The correlation here that is very important for me is that since I got appointed in Jyväskylä, Finland has been non-stop the happiest country in the world. So my work is definitely making impact, even if this might not be true. So the work I'm going to present today is by the individuals shown below. You have already seen Jussi and Johannes, who were here until yesterday. But when they knew I was going to talk, I guess they just thought, okay, let's get out of here. And in this audience, I don't really have to linger too long on the concept of what is an optical cavity. When I speak for chemists, I do have to do that. But here, it's sufficient to say that we can make cavities, and not by going to the local IKEA and putting the mirrors very close together, but of course we nanofabricate this type of structures. Then when we put molecules, let's first look at a molecule separately. So we have been talking about molecules very often in the context of quantum emitters. I think they're pretty lousy quantum emitters, most of them. And the reason is that while you can draw on a screen something like this, like a two-level system with a specific, in this case, excitation energy between the electronic ground and the electronic excited state, these are actually just points on the potential energy surface. Yeah? If I now I can just reach it, fortunately. If I start now fiddling around with one of these atoms, that energy can go down or up. Likewise, when I electronically excite the molecule, that energy can also change. So these are just points on the potential energy surface. And photoreactivity simply means that in the excited state, in the electronic excited state, turning around some of these atoms will lower the energy. And in fact, the reason that you can see me is because that's happening all of the time in your eyes. Now, this is where I come from, photochemistry. And what kind of got me into the rabbit hole were some early papers, or actually still, this is the kind of graphs that you see in polaritonic chemistry papers, where then, you get the formation of the upper and the lower polariton because of the strong light matter coupling. And then again, I can do the same trick. I can again now turn around this nitrogen group, and I will also change the energy in the ground in excited state because this is a light matter state. I mean, the matter still plays a role. Now, that's the key of catalysis. If I can change the potential energy surface, I can kind of force the wave packet that represents the atomic motions. I can kind of steer it, can control it. So when I saw this, I got super enthusiastic because now I could use all the stuff that we had been developing for looking at photochemistry under, super weak coupling conditions. We could now do it in a cavity and this way find ways to control chemistry. Looks fantastic in proposal. You can claim, sustainable this, sustainable that. Very nice. Importantly, you have control parameters. You can control that splitting through its Rabi splitting. Yeah, that's the difference. We know that. It's proportional to the dipole moment and the square root of the mode volume. Now, it's not that easy to control the mode volume. We saw a very nice example, but that's the kind of stuff that I am unable to do. Of course, what you get this hybrid states, and you have the dipole moment. Now, that's also something you cannot really control that easily because it's given by the molecule. So this whole concept of controlling, if you cannot control the mode volume, it's limited still. And what's more, if you want to do this, we have to go to plasmonic cavities. We have heard talks about that also this morning and just a minute ago. You need to fabricate something, and that's messy. People have succeeded in doing so. These are not our examples, but people have, for example, managed to put two gold spheres together by DNA origami type ideas, and this way get molecules into this mode volume. But it is all very difficult to scale up to something industrial. So if you want to save the planet, you have to think of something better. Also, the experiments that inspired me to work onto this, they always reach a strong coupling regime by coupling more than one molecule. So you couple a very large number of molecules, then you get collective coupling, and suddenly your Rabi splitting scales also with the number of molecules, or in this case, concentration. And that is a very easy control knob, a concentration. Yeah, you can vary that quite easily. So now you have the control knob, but now there is one speciality is that now your excited state becomes delocalized over all the molecules in a way. That sounds cool, but that is problematic for chemistry. And the other thing is that you get these dark states. That means that if you have n molecules, in principle coupling to a single cavity mode, as in this example for simplicity, you're going to have n minus 1 dark states, because that's the remainder of the states. And to quote that person over there, do not underestimate the power of these dark states, because they mess up the beautiful picture that I was trying to sell you before. Now, when I started working on this, I read the papers, I saw the spectra, I didn't understand it. And of course, when everything else fails, you can also read the manual, in this case the papers, but you can also just try something, because students are cheap. So Mikkel Kauto, he joined me and Jussis' group, and then the first thing that I wanted to see if it's really true. I'm quite skeptical. So he went out to He went out to create optical cavities. You can see the picture there. Now, to this audience, not a surprise. The cavity was done such that the transmission matches nicely the absorption spectrum of rhodamine 6G, commercial dye. And lo and behold, when you put a certain concentration of rhodamine in, you can reach strong coupling, and you put more molecules in, you get more strong coupling. So at this point I thought, okay, must be true, these polaritons are there, we can optically see them. Now let's think about what happens to the chemistry. And this is where things got messy and also exciting, because I started working on this because of papers started appearing in the literature where people were making claims that you can use this optical cavity to control photochemistry, that you can use optical cavities to control even ground state chemistry. In that case, you're not coupling anymore to an electronic transition, but you're going to couple to a vibrational transition. And lots of papers appeared where transport was shown to be enhanced of both charge and of excitation energy. So this was all pretty exciting, that suddenly there is a new way of doing catalysis, of controlling chemistry. So I wanted to have part of the cake and try to understand it. But as I'm a computational chemist or theoretical chemist by training, the question is not only does it work in experiment, but does it also work in theory? And the answer is, okay, people can disagree with me, and we can fight about it if you want. My opinion, it doesn't work in the theory. There is not a consistent theoretical framework that allows us to predict what kind of optical cavity structure do you need to make to control the chemistry. There is a lot of papers that post-predict stuff, but that's easy. But to predict stuff, I haven't seen one. And the ones who have tried to predict something, they fail when you try to increase a little bit the realism. So both for ground and excited state chemistry changes, I maintain there is no explanation. Transport, to end this on a positive note, I think there several computational and theoretical groups, including us, do agree now on the mechanism by which you can enhance transport on the strong matter coupling, but that's photophysics. That's not photochemistry. So my doubt is with the photochemistry, and I think at this point, I think it's also fair to ask, did it actually work in experiment? Because there's a huge reproducibility crisis. Some of these papers, when you try to do it yourself, I bet for a crate of beer, you're probably not going to find it. I mean, that is a little bit the tendency in this field, that it is very difficult to reproduce. And of course, if something doesn't work, it's difficult to publish. So we kind of left over with a publication bias view of the reality. But I don't know. I hope it works. But at the moment, I think it's fair to ask, did it work? And the challenge is, of course, that chemistry is something local. These polaritons are delocalized. You have the excitation shared in the ideal picture between all the molecules in the cavity modes. But chemistry is something that one molecule decides to do. Not all of them at the same time. So this is a typical example where you have the nice delocalized polaritonic state, and then one of these molecules decides to do a chemical reaction. So how does this even work? Because in this delocalized picture, each molecule is like 1/n square root of it excited. That's very little excited. That is kind of going to the bar too early on Monday evening. Nobody's really excited. So that is the challenge, right? I mean, how do we resolve this paradox? And for that, we need models. We know the interactions, we have seen many examples of Hamiltonians, and they're all more or less the same. They give you the same physics. But the question is now, how do we really model this? So we need something that can treat a large number of molecules, but chemically accurate. And the way we try to do this is that the chemical accuracy, well, we get from quantum chemistry, or in this case, we're using a model which combines quantum chemistry. That is, you treat the electronic degrees of freedom, you treat by quantum mechanics, and your nuclei, you still treat by classical mechanics. In this case, I'll come to that later. And then the rest of the system, which is not really involved directly in the photoexcitation, you treat with so-called molecular mechanics. And molecular mechanics is basically a bunch of simple functions that correspond to chemical intuitive concepts. You have a bond, which is described by harmonic potential. Then you have van der Waals interactions, which are described by some other model potential. And then you parameterize that very heavily. And now force fields for, let's say, proteins, for example, are much better than any DFT method can ever get, because they have been overfitted most likely. But this allows us to treat millions of atoms quite straightforwardly. When I started this field of this combining these two models, it was always received with a lot of criticism and well, skepsis. But since it got the Nobel Prize in 2013, I don't have to worry about that anymore. The next thing is we want to treat many molecules. And for computationalist chemists, Finland is a great country because we have really extremely excellent resources for doing computation. This is a picture of the type of computer we have standing in Kajani. What is a nice little thing to say about this computer is that it has a negative carbon footprint. That means, well, the reason why is that it's hydropower that is driving the electricity, and at the same time the heat from the components is not used to waste, but it is used to heat up the people up there. And it's further north, so they need it more than us at the moment. And that means that the city doesn't need to burn any fossil fuels in order to keep the people hot. The computers do it for them. So even if I compute something which is totally rubbish, and you're free to say that, I'm still saving the planet, and I think that's good to know. Now, the model that we describe the interaction, to describe the interaction between the confined light modes and the molecules, is we start from Born-Oppenheimer. That is, we treat the fast degrees of freedom by quantum mechanics. In this case, those will be the cavity modes and the electronic degrees of freedom. And for those, we use one of the standard models that has come by many times in this meeting already, the Tevis-Cummings model, but now it depends parametrically on the positions of the atoms, just like in the standard Born-Oppenheimer. So what we get is we have the molecular excitation energy operator that is depending parametrically now on the molecules because the position of the atoms determines the excitation energy. Then there's the cavity mode part, then there's the interaction part, and again, the dipole moment of the molecules as well as the electromagnetic field magnitude now depend on the position of the atoms in your system. So that is how we kind of separate these 2 degrees of freedom. And then on the end, we add the ground state energy of all the molecules because this looks at the excitation energy. So the excited state energy is the ground state energy plus the excitation energy, of course. What we do not do, I often get that question, but what we do not do is we do not explicitly model the mirrors. So Johannes Feist was giving yesterday a beautiful talk about how to actually quantize electromagnetic fields starting from Maxwell's equation. That is also how we do it. So we're not modeling the explicit atoms of the mirrors and so on, but the only thing we model is the field that is the quantized fields that are at the positions of the molecules. All right? That means that depending on the kind of structure that you want to model for confining light, the only thing you need to be able to find out is what is the field at the molecules. So you need to quantize the field, and then you can go ahead. And for that, we have done something very simple, like for plasmonic cavities. We can also do it for, what is that? A plasmonic cavity, plasmonic lattice, block surface waves, and we can also do it for nanocavities. This is a picture from the famous Baumberg paper. This is what it looked like in the picture. This is what it looked like if you really want to model this atomistically. It's a bit more ugly and a bit more difficult to work on, but this is how we do these things. So we're not combining Maxwell with MD, but we use these quantization methods. All right. Then the cavity modes have finite lifetime, so we add losses. That makes our Hamiltonian non-Hermitian. We will talk about that this morning as well. That makes the computation far more expensive, unfortunately, but it's what we have to do. And then we treat the molecular degrees of freedom basically by classical mechanics, Newton's equations of motion. And then the trick is, how do the classical and the quantum part talk to each other? And about that trick, I could give probably a whole workshop. Lots of methods have been invented to do this some way or the other. The bottom line is that we propagate the quantum system, which consists of the photons of the cavity and the molecular excitations and the coupling, and the nuclear degrees of freedom along with each other, and they talk to each other. The atoms feel run on a potential energy surface that is provided by the quantum degrees of freedom, and the quantum degrees of freedom are propagated along these classical molecular dynamics trajectories. Now, the first thing that we were interested in very for long is it possible to control photochemistry with the cavity? And one of the first things that really puzzled us in the papers that had been published so far is that all the reactions that were claimed to be changed by putting them in an optical cavity, they happen much slower than the cavity than the polariton lifetime. That was always a bit strange to me. How can a reaction that takes a few hundred picoseconds be affected by something that lives only a few femtoseconds? So we then looked in the literature for fast reactions, and what we could come up with was this molecule. I'm not going to pronounce it, although I am a chemist and therefore qualified to say what it is. I just call it HBQ. And this HBQ molecule, as you can see, there is a bond breaking. That proton is transferred. When the molecule gets excited, that proton from the red oxygen is very quickly transferred towards the blue nitrogen. And that is accompanied by a very large shift in energy gap between the ground and excited state. So from the fluorescence, the very red-shifted fluorescence, you can see that the reaction is happening. And the first thing we did before we did even the experiments was to try to understand, can we understand if there is any cavity effect from our simulations. So we can do an MD simulation. So here I show you just a snapshot. I take away our solvent, cyclohexane, so that you only see the molecule now. And I'm going to just run a short, show you an animation of a trajectory. So one thing is, whenever I do a project, the first thing I ask myself, can I make an animation? And if the answer is yes, good project. Not, then look for another project. A few words. I don't think there's any quantum chemists in the room, are there? Okay, then this is really accurate. But if it was for quantum chemists, this is not very accurate. I mean, in quantum chemistry, the rule of the thumb is the longer the acronym, the better it is. This is a really short acronym, just 3 letters and then some crappy DFT functional and then a small basis set. But it doesn't really matter. I mean, in the quantum chemistry audience, I would probably hide this aspect and hope nobody asks. But here I dare. The point is that this gives us a qualitatively correct picture in the sense that this is in line with what you experimentally would observe for this molecule. So let's start it. So in first, we see a little bit of wiggling and jiggling in the ground state. Then at 100 femtoseconds, I'm going to excite the system. That is now, and indeed, within 10 femtoseconds or so, that proton jumps to the other side. Now, this was nice because something moved. If you want to show it in a little bit more 2D type representation, what happens is basically the excited state, the electronic excited state, the potential energy surface along the reaction coordinate describing that motion of the proton is just down the hill. It's like you go up the mountain and you slide down without any barrier. That is why it's so fast. Now with this, we then started thinking about what could the cavity do. And the prevailing paradigm at the time was that, well, cavities can suppress photochemical reactivity because when the polariton forms, and the Rabi splitting goes like the square root of the concentration, the more molecules I start putting into my optical cavity, then at this Franconen region, so where the molecular absorption is taking place, that is the transition that you couple. So there is where you create a strong coupling situation. In this plot, what I'm doing, I vary the number of molecules from whatever it is, 256 to 1024. And then I take one molecule and I just calculate the minimum energy that I need to transfer that proton from here to there. So basically one molecule, they're all coupled, and then one molecule has to undergo the reaction. And in order to do so, if the coupling gets stronger and stronger, the Rabi splitting at the Franconen region gets larger and larger, the barrier gets higher and higher, and it was then the hypothesis that strong coupling will suppress a photochemical reaction. Now, this is definitely true at 0 Kelvin, but even in US, that is very rare in the winter also. So most of the time it's a bit hotter. So the question is now, what happens with this model, this idea, when you do this at room temperature? So what we do, well, here are some details of the simulation. We basically can choose our cavity field strength such that with ranging between 100 molecules and 2,000 molecules, we can reach strong coupling. And then we can start systematically asking ourselves the question, at what coupling strengths do we see such suppression? Is such suppression happening at all, yes or no? Now, what I'm going to show you here is a result from a classical MD trajectory. So we run these trajectories in the ground state. So we have like a room temperature, Boltzmann-weighted ensemble of structures. And then we can, in each of these structures that we extract from our trajectory, we can calculate what's the excitation energy. And what you get is in blue is a spectrum. This spectrum does not have the vibronic progression that you would expect from a real molecule. And that is because of its classical dynamics of the nucleus. So you don't have it. The fact that you have something Gaussian-like is therefore a good sign, because it means you kind of reach ergodicity, you're kind of sampling things quite well. And then if we take this ensemble of bare HBQ molecules, and I think this pink line is for 500 something molecules. I take these 500 something molecules from the trajectory, I copy them and put them in my optical cavity system. Then I get indeed strong coupling. I see the mode splits and have an upper and a lower polariton. And then the question is, if you now photoexcite this upper or lower polariton, do you see any differences with respect to the situation if the molecule is not in the cavity? So that is what I'm trying to plot here. So what I'm plotting here is for a 500 or so molecule ensemble. They're all coupled, they're all between the mirrors. And then I see the plot basically as a function of time, the distance of the proton to the oxygen. And what you can see is that immediately one of these 500 something molecules undergoes the reaction. So I'm not suppressing it. And this happens, doesn't really matter. We assume we have continuous wave excitation. We can excite here, we can excite there. All these little arrows indicate an eigenstate in which we start our simulation. So there is no suppression of this photochemical reaction, even though we have reached strong coupling. And the question is then, why is that? Well, I'm coming to that in a moment, but basically what the polariton seems to do, it just seems to act like a very expensive filter through which you're exciting your molecules. And this is due to the disorder that you have for this kind of molecules. I mean, the line width of the absorption spectrum for a molecule is not the inhomogeneous line, it's the inhomogeneous line width. It's the fact that each molecule is slightly different, is in a slightly different environment, and therefore absorbs slightly different energies. As I said, it's unavoidable. That leads to the line width. And what I'm showing you here is you can then start increasing the number of molecules, but this gray stuff, the absorption spectrum of the molecule without mirrors, that basically determines your density of states. So we have always, even in the largest Rabi splitting, we always have overlap between our polariton bands and our dark states. And as a consequence of that, none of these polaritonic states is actually the beautiful picture of fully delocalized excitation between the cavity and the molecules. Instead, here I'm plotting the photon contribution to each of the states for 128 molecules up the way to 2000 molecules. And you can see that always these states are, that the photon is smeared out over all the states. So all the states, there is no dark states, there is no bright states. All the states are like the weather at the moment. They're all gray. And because they're all gray, even though they have absorption strength, they have oscillator strength, but very little because the photon contribution is small. So yes, you do get this nice double peak absorption, but none of the states that actually absorbs is that delocalized polaritonic state that we were talking about in the beginning. They're all just molecular state with a small contribution from the cavity photon. So when you excite them, this molecule is maybe 95% excited. That's enough to get the party going. So these molecules then start doing the reaction. If you want to reach if you want to suppress it, I mean, you can do that. But in that case, you need to go to the so-called ultra-strong coupling, which is for some reason arbitrarily said to be more than 10% of the excitation energy. Then you can do this, and what I'm plotting here is basically the number of dark states divided by the number of polaritonic states. So if you have 500 molecules, you ideally would get 249 dark. No, you get 500 minus 1 divided by 2. Yes, wait a minute. So we have 2 polaritonic states, and we have 500 minus 1 dark state. So if I divide them, then you get 250. So what you can see in this plot, sorry for that little loss here, is that when you start increasing the Rabi splitting, then this ratio starts approaching and then in the end settling to that number. So that only when the coupling becomes large enough, sure, then you get your polaritonic state, and then you suppress the photochemistry. But in that situation, this is trivial. And the reason why I believe it's trivial is that what happens then is that your combined molecule cavity absorption is actually exceeding the molecular absorption. So let's say that your molecule absorbs around 400, and then you can reach this ultra-strong coupling regime, and maybe you get it all the way down to 500 nanometer. I'm just making up a number now. And then you say, oh, now I suppress the chemistry. But the molecule wasn't absorbing at 500 nanometer to begin with. So if you want to protect the molecule against 500 nanometer light, you don't need to do anything. I mean, building a cavity around it is a very expensive way of keeping yourself busy, I would say. But anyway, if you do go there, if you do go to this ultra-strong coupling regime, then all the protons stay where they're supposed to be, and there is a suppression of the reaction. But again, yeah, it just means that you now have created an absorption where the molecule wasn't absorbing in the first place. So that is not so interesting, in my opinion. Okay, then to test this idea of this polaritonic optical filtering experimentally, we built these cavities, so together with Jussi. So what we have here, we have a aluminium bottom mirror. Yeah, we're going to make a cavity in the UV. We have an aluminium bottom mirror. We put the molecule in a PMMA film. This is the absorption of the molecule. This is our emission of the molecule. We couple these UV transitions, and we use a very thin top mirror. That means that our fluorescence of the photo product is simply leaking out of the cavity, just like that. So that means we can now probe the fluorescence as a way to know that the reaction is happening. And then we put our cavity sample on a rotating stage so that we can actually scan as a function of incident angle the reflection, and from that infer the absorption, and we can measure the emission with a spectrometer at the same time. And what you then measure is this kind of messy 2D plots. We have seen many of them coming by. The theory always looks beautiful. Experiment always looks like, nah, we have to, that's it. But what you can see, hopefully, is that, there is some signature of the strong coupling there. We have a avoided crossing. In dotted black, the black dotted lines is the cavity mode, which we obtained from this coupled harmonic oscillator model. And then the black vertical ones, no, sorry, this one. The horizontal ones, those are the molecular absorption. And then in these white dashed lines, we have the polaritons from the coupled harmonic oscillator fitting. So yes, we have some coupling. It's not very strong, but we're still in the strong coupling regime because we see our avoided crossing. And then, in order to test the conjecture that we obtained from the MD simulation, based on the MD simulation, that these polaritons simply act as filters, then we figured out that in that case, your excitation spectrum, so that's a spectrum where you look at the fluorescence, you fix your detector at a certain wavelength, and then you start scanning the excitation energy, and it tells you something about which portions of the molecular excitation lead to that product. You scan the excitation energy, and that is an excitation spectrum. That excitation spectrum is relatively easy to measure for the molecules. It's a bit more complicated to measure for the optical cavity system. But our conjecture is that if it's optical filtering, then if you have the excitation spectrum of the molecule convoluted with the absorption spectrum of the polaritonic system, you should predict the excitation spectrum of the cavity. So basically, we have here the absorption spectrum, and it's all a little bit messy, unfortunately, but that's the experimental reality in these systems. Then we have the excitation spectrum of the film, so it's just the bare molecules embedded in the PMMA film, and then convoluting them, or in this case, taking the product of the two of them, gives us our predicted cavity excitation spectrum. Oh, not yet. That one. And if we then measure the cavity excitation spectrum, that's exactly what we get. I'm only showing 3 angles for one concentration cavity, but if you collect them all together and you feel the pressure of publishing because students have to graduate, then you start believing this is all the same, and the whole effect of the optical cavity is just a filter. I could have excited my cuvette straight through the optical cavity. It's a very expensive filter though, straight to the optical cavity and get the reaction done according to molecules just being excited via that filter. So that's not so good, in my opinion. But at the moment, there is a little bit of hope at the end of the tunnel. I hope the light is not that light, but we believe now that we can, or not believe yet, but we hypothesize now that we can actually use polaritonic modes to actually channel energy somewhere. But that's again photophysics. We're not changing chemistry, we're just changing kind of the selection rules a bit. And that could still be very interesting, but that is hopefully for the next conference if that ever takes place. Then I have a few more minutes, so I wanted to end it on a positive note, not that all polaritonic chemistry is bad. I think exciton transport is a chemical, photophysical process that's very important for photovoltaics. Yeah, you want to catch the light and then you want to transfer it to some interface. So if you can enhance that, that will be good. Another take-home message from this is that once you have something working, you can milk it out and you can keep on publishing it as long as it is hot. Now the temperature is cooling down, so it's not so easy anymore. The impact factors of the journals go down, but okay. But anyway, what I want to say with this is that this is not only coming from semi-classical dynamics. We can now also do it fully quantum mechanical. So we no longer need classical mechanics for our nuclei, but we can also treat them quantum mechanical, and it leads to the same conclusions, same findings. So I think this is something where we have predictive power at the moment. And the experiment that I want to refer to today and do simulations for is an experiment by Tal Schwarz, where they couple molecules, in this case J aggregates, so not really molecule, but they couple these J aggregate systems to the top of a Bragg mirror. and then the block surface wave which forms there, which confines the light there, couples to these excitations in the J aggregates. That is shown on this plot. So the light line, the vacuum line is the red one, the block surface wave is the white one, and then if you have the J aggregates, which are exciting energies over there, you get this lower polariton. And then what they do is they're exciting one of the J aggregates on top of the mirror, and then they monitor with microscopy, K-dependent microscopy, they can monitor basically what the wave packet is doing. And what they see, what you can see on the scale bar over there, on a 100 femtosecond time scale, you already travel micrometers far away. So that's cool. If we can really make this work and connect molecules like that and really transport that energy from one side to the other side with this speed, with the speed of light, I think that was the name of that paper, that's something useful. But do we understand it? And in order to understand it, we then try to model that system. Unfortunately, we don't really know how to accurately describe a J aggregate, so we took another molecule that we put on top of this Bragg mirror. Then we describe the dispersion that is shown in that plot. So the Bragg mirror dispersion, the block surface wave dispersion is this line that goes like this. The molecular excitation is the horizontal line. We exciting the central molecule of this, I don't know how many, I think there was 1,000 molecules of that. We excite the central one, or maybe 1,001 to have a central one. And then we look at how does the wave packet propagate. And we do see in our simulations, that is the position of the molecules versus the time, we do see that excitation, that wave packet moves, it spreads out. But it's clearly not ballistic. If it were ballistic, you would only see these two dotted lines, which is basically indicating the speed of light, the maximum group velocity of the lower group, of the lower polariton dispersion. But it's some kind of mixture of the two. So what we see is we have both something that looks like diffusion, something that looks like ballistic motion. We have an explanation for that. That is that these, again, do not underestimate the power of these dark states. There is all the time reversible energy transfer between dark states and bright states. The bright states move, then go back in the dark states. We don't move. Then after a while, we go back in the bright states and we move again. It's this. This is what gives rise to diffusion. And in order to analyze that in a bit more detail, we try to do the same thing as Tal Schwarz and his people. So we start analyzing now the transport as a function of the K vector. So basically, I can make little windows on my dispersion and basically look at how does the transport in that window look like for these K vectors. And then you see that when the state is quite photonic, so low in energy, then it's pretty it's much more ballistic than if you go higher up in energy and you're close to the exciton resonances. And you can also do this quantitatively, because this is, of course, you see nothing basically. And quantitatively is just fit it to the diffusion equation. If the coefficient here of the mean square displacement, which is now shown for these two windows over there, if the fit of the coefficient of the t of the time is the beta is quadratic, then it's ballistic. If it is 1, then it's diffusion. It is standard, I don't know, MSD knowledge, mean square displacement knowledge. And indeed, when we do that, we see that if the photonic content of the system is higher, is lower, then we get more and more diffusion. And if the photonic component of the polaritons get higher, we get more ballistic motion. And that is nicely in line with the experiment, not perfect, but it is there. And importantly, in the last plot, I'm showing what the majority of people is doing, where you just take a two-level system and add some disorder, like site disorder, you don't get that transition. So you really need vibrations to actually get that thing correct. So with that, I think I'm summarizing. So we cooked together some kind of a model so that we can actually simulate with some chemical accuracy for a large number of molecules coupled to an optical cavity. At the moment, we can actually go up to millions of molecules with some tricks. The method is based on Born-Oppenheimer, and I've shown you two applications. One in which we try to understand what's the effect of strong coupling on an ultra-fast photochemical reaction, none. And the second is what's the effect of strong coupling on transport, and that was pretty high. And although I'm at the end of my time, some take-home messages. Polaritonic chemistry has a reproducibility crisis. It's very difficult to reproduce, or you have to go to conferences to hear, oh, I tried that. We tried that, and we also haven't published that. Of course, we know why that is. It's us who does that, because we are the reviewers. We are often the editors for journals. We don't like to publish negative results. Now, to solve that problem, we should just have a new journal, the Journal of Polaritonics, negative results. If you have negative results, no IPC. If you have positive results, that jackpot APC, because then you're one step closer to the Nobel Prize. That's my thinking. For us, doing theory and computation, I mean, we should maybe go away from post-diction and say that you can explain something after the experimentalist has shown you the data. We should go to prediction and tell them what they should measure. and then be right or wrong. And we should have an estimate of the. We still don't even know how big this effect will be. I mean, even if it's true, if the effect is a few kT, then this is maybe not worth doing. And then finally, polar electronic chemistry is exciting. I hope it's true, but I'm not so sure. Polar electronic physics, I think, is pretty well true. I mean, we have seen the whole conference. We have seen, well, I should have, didn't fit more examples, but we have seen all beautiful examples where things do work. But that's physics, in my opinion, not chemistry. Chemistry means bond breaks, and that is not affected, it seems. And with that, I'd like to thank my collaborators, co-workers, victims, and so on, heroes. The red ones are involved in the project, and the funding agencies that made it possible. And of course, I would like to thank you for attention, and if there are questions, I'm happy to answer them in the last 35 seconds.
Thank you for this. Thank you for this exciting talk. Is there a short question or comment? Go ahead.
Thank you, Gerrit, for your talk. Just also a question regarding, since this reaction, they should appear only on a few molecule size, and your people are making these cavities with many molecules that are completely delocalized. To maybe corner a bit more this problem, wouldn't it be actually interesting also to work in the few molecule range with smaller mode volumes and less molecules, and maybe see if there is something going on there?
Yes. Yeah, that is so I think most of our current funding is all, we all promised that. So we are looking into that, also try to model it. So with Johannes Feist, that is where we're interested in his few mode quantization method to really model explicitly what a gap between two nanoparticles, what kind of effect it would have on the chemistry. And then let's see if someone, or maybe us, can fabricate it. So that is indeed the goal. I mean, we need to meet in the middle. We need to meet somewhere where theoretically we can be confident that we can describe that number of molecules with sufficient accuracy, while from the experimental side, we must be confident that we can indeed model that number of molecules strongly coupled, and then see whether there are changes to the chemistry. That is indeed my dream, to go into that direction. But of course, as you also mentioned, even though your system doesn't seem to have it, and that is interesting, the Q factor is the problem there. With ordinary plasmonics, and yeah, you have mentioned it, many people have mentioned that lifetimes are a bit short, are too short for any meaningful chemical reaction, although this proton transfer, that is fast. So it would be great if we could somehow get that into Jeremy Baumbach's methylene, cucurbitryl, and then couple that to the nanoparticle mirror system, for example, or get it inside of your system. Okay, that's what.
Thank you. Okay, I think we can close the session with this. Let's thank the speakers again. And I guess there will be some coffee there. Yes.